What if I told you that the stars you've been looking at your whole life could kill you instantly? Not in years, not in minutes, in seconds. One wrong distance, one powerful burst of energy, and Earth wouldn't just be damaged, it would be completely erased. And the scariest part? Some of these stars are already unstable, already dying, and we might not even see it coming. The most beautiful things in the universe are also the most dangerous. Look up on a clear night and you will see them, scattered across the darkness like salt thrown on black velvet, cold and quiet and impossibly distant. They have inspired poetry and navigation and religion and science. Every culture that has ever existed on this planet has looked up at the same stars and found meaning in them. They have guided sailors home across featureless oceans. They have marked the seasons for farmers. They have been the backdrop of every love story told under an open sky. And every single one of them is capable of killing you. Not metaphorically, not philosophically, literally, physically, completely, and in several different ways depending on which star you are unlucky enough to be near when it decides to do something catastrophic. Stars are not the gentle lanterns of the night sky that poetry has always made them out to be. They are thermonuclear furnaces of incomprehensible scale, held together by gravity and constantly trying to tear themselves apart through the explosive force of fusion. They are unstable. They are violent. They age, and when they age badly, they do so with a ferocity that can sterilize entire solar systems, erase planetary atmospheres, and send radiation across thousands of light years with enough energy to end every living thing on a world that never saw it coming. The universe is beautiful. The universe is also trying to kill you, and the stars are its most elegant weapons. Let us begin with the obvious one, the sun, your sun. The warm, familiar, life-giving star that rises every morning and makes plants grow and keeps the oceans liquid and provides the energy that powers every food chain on the planet. The star that has been called Ra and Apollo and Sol and 1,000 other names by 1,000 other cultures across human history. The star that feels, from this comfortable distance of 150 million kilometers, like a benevolent presence. The sun is a nuclear bomb 1.4 million kilometers across that has been continuously detonating for 4.6 billion years. Every second, it converts approximately 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to billions of nuclear weapons simultaneously. The only reason this process does not instantly destroy everything in the solar system is that the sun is also enormous enough for its own gravity to contain most of that energy, releasing it gradually as light and heat rather than all at once as an explosion. But the sun does not always behave. Occasionally, triggered by disturbances in its magnetic field, by the roiling convection of plasma beneath its surface, by processes that solar physicists understand imperfectly and cannot yet reliably predict, the sun releases what are called solar flares and coronal mass ejections. A solar flare is a sudden, intense burst of radiation across the electromagnetic spectrum. A coronal mass ejection is a billion-ton cloud of magnetized plasma hurled into space at millions of kilometers per hour. When these events are directed toward Earth, they interact with our planet's magnetic field and atmosphere. Mild events produce auroras, the northern and southern lights, one of the most beautiful phenomena visible from Earth's surface. Stronger events can disrupt radio communications, damage satellites, and interfere with power grids. The most powerful events on record can do considerably more. In 1859, a solar storm, now called the Carrington event, struck Earth with such force that telegraph systems across Europe and North America failed catastrophically. Some telegraph operators reported receiving electric shocks, and telegraph paper spontaneously caught fire. Auroras were visible as far south as the Caribbean. The night sky in parts of the United States was bright enough to read by. The Carrington event happened when the most sophisticated technology on Earth was the telegraph. If an equivalent storm struck tomorrow, it would hit a civilization that runs on electricity. A civilization whose power grids, internet infrastructure, satellite networks, financial systems, hospital equipment, water treatment facilities, and food distribution logistics all depend entirely on electrical systems. The estimated damage from a Carrington-scale event today ranges from $1 to several trillion, with recovery times of months to years. In the most severe scenarios, the cascading failure of interconnected systems could produce consequences that the word catastrophic is not quite large enough to contain. The sun has done this before. It will do it again. The question is not whether, but when, and whether we will be ready. Move further out. Beyond our solar system, across the galaxy, there are stars aging toward their ends. And when massive stars die, they do not go quietly. They go supernova, collapsing inward in a fraction of a second and then rebounding in an explosion so violent that for a brief time, a single star outshines an entire galaxy of hundreds of billions of stars. A supernova releases, in its first moments, more energy than the sun will produce over its entire 10 billion-year lifetime. Much of this energy comes in the form of neutrinos, ghostly, nearly massless particles that interact almost not at all with ordinary matter. Neutrinos pass through the Earth as though it were not there. A supernova at close range would bathe everything in a neutrino flux so intense that even these near undetectable particles would cause measurable biological damage. But the more pressing danger from a nearby supernova is gamma radiation. Gamma rays are the most energetic form of electromagnetic radiation, high-energy photons capable of penetrating almost any material and ionizing the atoms they pass through. A supernova within roughly 25 to 50 light-years of Earth would deliver a gamma-ray dose sufficient to strip away significant portions of Earth's ozone layer, the thin atmospheric shield that blocks ultraviolet radiation from the sun. Without the ozone layer, UV radiation from our own sun, normally benign at Earth's surface because of that protection, would reach the ground at lethal intensities. DNA is exquisitely sensitive to UV damage. Photosynthesis would be disrupted. Marine food chains, which depend on phytoplankton near the ocean surface, would collapse. Terrestrial ecosystems would follow. A supernova does not need to be close enough to cook you directly. It only needs to be close enough to remove the shield that has been protecting you all along. And then your own sun does the rest. Some scientists have proposed that one or more mass extinction events in Earth's history, periods when large percentages of all species on Earth vanished within geologically brief intervals, may have been caused or contributed to by nearby supernovae. The evidence is suggestive but not conclusive. What is clear is that supernovae happen, that the galaxy is full of stars capable of producing them, and that the distances involved are large but not infinite. The nearest star considered a serious supernova candidate within the relevant danger zone is Ik Pegasi, approximately 150 light-years away. It is a binary system in which one component is a white dwarf accumulating material from its companion star. Exactly the configuration that can produce a Type 1a supernova when the white dwarf's mass exceeds a critical threshold. Astronomers do not believe Ik Pegasi is an immediate threat, but the universe does not consult astronomers before doing anything. If supernovae are dangerous, gamma-ray bursts are in a different category entirely. They are the most energetic explosions known to occur in the universe, and they release almost all of their energy as the name suggests, gamma rays, in focused beams that travel across billions of light-years without significantly dispersing. Gamma-ray bursts come in two varieties. Short gamma-ray bursts last less than 2 seconds and are produced by the collision of two neutron stars, or a neutron star and a black hole. Long gamma-ray bursts last from a few seconds to several minutes and are produced by the collapse of the most massive stars. Events called hypernovae or collapsars. In both cases, the energy released is staggering beyond easy description. A gamma-ray burst can, in a few seconds, release more energy than the sun will produce in its entire lifetime. Some release more energy than entire galaxies produce in a year. The beam of a gamma-ray burst is narrow, typically a few degrees wide, which means that most bursts we detect are pointed away from us and simply illuminate our instruments as they pass through the universe harmlessly. But if a gamma-ray burst were close enough and pointed directly at Earth, the consequences would be severe. Models suggest that a gamma-ray burst within a few kiloparsecs, a few thousand light-years, aimed at Earth could devastate the ozone layer far more thoroughly than any supernova, potentially removing up to 90% of it over a span of years. The subsequent UV exposure would be sufficient to cause a mass extinction event of the first order. Intriguingly, the Ordovician mass extinction, which occurred approximately 440 million years ago and wiped out roughly 85% of all species on Earth, has been proposed by some researchers as a potential gamma-ray burst event. The extinction pattern shows a bias toward organisms that lived near the ocean surface, where UV exposure would have been greatest, while deeper water species fared somewhat better. This is exactly the pattern you would predict from ozone depletion, followed by elevated UV radiation. We may have been hit before. Gamma-ray bursts are detected at a rate of roughly 1 per day across the observable universe. The universe is large and bursts are brief, so the probability of a dangerous one hitting Earth at any given time is extremely low. But the universe is also very old and very large, and extremely low probabilities given enough time have a way of eventually coming true. Stars move. The galaxy is not static. Every star within it is orbiting the galactic center, and those orbits are not perfectly stable. Stars drift, their paths shifting slowly over millions of years under the influence of gravity from neighboring stars, molecular clouds, and the overall galactic mass distribution. Every few million years, a star passes close enough to the solar system to disturb the Oort cloud, the vast, distant shell of comets surrounding the solar system at distances up to 100,000 astronomical units from the Sun. When a passing star gravitationally perturbs the Oort cloud, it can redirect comets from their stable, distant orbits into the inner solar system, toward the planets, toward Earth. This is not a hypothetical risk. It is a measured, ongoing process. Astronomers using data from the Gaia Space Observatory have identified dozens of stars that have passed within a few light-years of the Sun in the past few million years, and dozens more that will do so in the future. In approximately 1.4 million years, a star called Gliese 710 will pass within roughly 0.2 light-years of the Sun, close enough to significantly perturb the Oort cloud and potentially send a wave of comets into the inner solar system over the following millions of years. A comet or asteroid large enough to trigger a mass extinction, arriving with no warning and at a trajectory determined by gravitational perturbations set in motion a million years ago by a passing star. This is a danger that originates not with our own Sun, but with the broader stellar neighborhood through which we are perpetually, slowly drifting. Of all the objects in the universe that could harm Earth from a great distance, magnetars may be the most alarming. A magnetar is a type of neutron star, the collapsed remnant of a massive star that exploded, with a magnetic field so powerful that it strains the capacity of language to describe. Earth's magnetic field is measured in microteslas. A typical neutron star's field is around 100 billion Tesla. A magnetar's field reaches 100 trillion Tesla, a quadrillion times stronger than Earth's. At these field strengths, the vacuum of space itself behaves differently. Magnetars are capable of releasing sudden, enormous bursts of gamma rays and X-rays called giant flares. Events triggered by starquakes, sudden shifts in the magnetar's crust caused by the enormous stresses of its magnetic field. These flares release, in a fraction of a second, more energy than the Sun releases in 100,000 years. In December 2004, a giant flare from a magnetar called SGR 1806-20 reached Earth. The magnetar was approximately 50,000 light-years away, on the other side of the galaxy. Despite that enormous distance, the flare was energetic enough to ionize Earth's upper atmosphere briefly and to saturate the detectors of multiple gamma-ray observatories worldwide. Instruments designed to measure the faint, distant signals of cosmic events simply saturated. They were overwhelmed, driven to their maximum readings for approximately 0.2 seconds. If that magnetar had been 10 light-years away instead of 50,000, the flare would have been catastrophic. If it had been within a few light-years, it would have been an extinction event. There are no known magnetars within dangerous range of Earth at present, but magnetars are not predictable. They do not announce their flares in advance. Their starquakes occur on timescales determined by the complex physics of ultra-dense matter under extreme magnetic stress, physics that is still not fully understood. Here is the honest conclusion. The universe is indifferent. The stars do not know you exist. The supernova that might one day threaten Earth is not aiming at us. It is simply exploding, doing what massive dying stars do. And the geometry of the galaxy will determine whether the beam passes harmlessly to one side or finds us in its path. The magnetar that sent a flare across 50,000 light-years in 2004 had no awareness of the small blue planet whose atmosphere it briefly ionized. It was simply being a magnetar. This indifference is, in a strange way, more frightening than malice would be. Malice can be negotiated with, reasoned with, deterred. Indifference simply proceeds. The universe has no category for human civilization, no register in which our existence is noted, no mechanism by which our survival influences the physics of stellar evolution. We are here, briefly, on a small, warm rock orbiting an average star, surrounded by a galaxy full of processes that could, on any given day, without warning, send something our way that we cannot stop and cannot survive. And yet, here we also are, a species that looked up at those same stars and built mathematics precise enough to calculate their distances, chemistry sophisticated enough to determine their composition, physics deep enough to explain their depths. We pointed telescopes at the sky and found the magnetars, and measured their fields and detected their flares. We tracked the path of Gliese 710 and calculated its closest approach to within fractions of a light-year. We photographed black holes and listened to gravitational waves and sent machines into interstellar space. We did not have to do any of this. The stars were not going to help us. We figured it out ourselves, in the dark, on a small rock, in the brief window of time we have been given. The stars may kill you, but they also made you. Every atom of carbon in your body, every atom of nitrogen and oxygen and iron, all of it was forged in stellar cores and scattered across the galaxy by stellar deaths, and eventually gathered by gravity into the world you stand on. The very processes that make stars dangerous are the processes that make life chemically possible. You are, in the most literal sense, a product of stellar violence. The supernovae that could end us are the same supernovae that built us. So look up tonight. Find them in the darkness. Those cold, distant points of light that have watched every human generation come and go, that burned before the first cell divided in the first ocean, that will burn long after the last human thought has faded. Know them for what they are, the most beautiful, the most ancient, and the most dangerous things the universe has ever made. And appreciate, with whatever part of you is capable of appreciation, that for now, for this moment, in this particular corner of the galaxy, on this improbable afternoon of cosmic time, they are just barely far enough away.